Now that you had a chance to take some basic notes and do some practice, let's collect this into a single cheat sheet. So ordinarily, you would not be able to use this type of thing on a test or quiz. Today is the exception, but if you want to use this moving forward, make sure you transfer these into your Cornell notes at some point. So let's talk first about parallel. Now, of course, when we're talking about parallel, we know the definition, but what we're looking for are same slopes. And so as long as you have the same slopes, excuse me, for two different lines, you can consider them parallel. So the procedure and technique is going to be pretty straightforward. We just have to find the slopes and then compare them. If they're the same, then they're parallel. If they're even a little bit different, then they're not. They're something else. So there's two basic ways we can do this. From points on the, if you have dealing with a graph, excuse me, or you're dealing just with a set of points, we have to acknowledge at some point that the slope formula is going to be change in y. Oh, what happened there? Change in y over change in x. And do recall those triangles refer to change in. The same thing as rise over run, okay? Or just overall rate of change. Okay? And so as long as you're using some definition, maybe you draw slope triangles. You should be able to determine your slope. Now there is a formula. The formula works best when you have just points, or you don't like counting with the technique above. And just for the record, the slope formula it is still change in y over change in x, but it has a very specific formula of y2 minus y1 over x2 minus x1. You don't see me use that very much because, frankly, in my real life, even after like, you know, 13 years of math in school plus all these years of been teaching, I just think that ultimately that's really confusing. And so I don't tend to like that version of it, but if that works for you, that works for you. Let's put this immediately into action. So the question of this, of course, are they parallel? Well, to determine their parallel, we need to determine their slopes. And so I'm going to go ahead and draw in some triangles here. And so often called slope triangles, this helps us determine our rise and our run. So we have this one here and this one there. So I know one triangle is bigger than the other, but that doesn't actually change what the slope values are going to be. So just because one's bigger than the other doesn't mean we automatically assume they're non-parallel. We have to do some counting. So we have, let's see, 1, 2, 3, 4, 5, 6. So that's plus 6 going to the right, and then we have 1, 2, 3, 4. We have minus 4 going down. And so for this triangle, we have change in y over change in x, which will just equate to plus 6 over minus 4. And keep in mind we have a minus here because we're going down. Actually, I'm going to change it around. So I made a very common error there. We have to go up and down before we go left and right. So it actually should be minus 4 over plus 6. Sorry about that. So minus 4 plus 6, very common mistake that I just made. So hopefully you don't make that too, because we have to go up and down before we go left and right. Since they're both even numbers, we can divide them both by 2, and we end up with a negative 2/3 for our slope. And so the slope for this line is going to be negative 2/3. And so all we have to do is compare it to the bottom one. Well, here we have a minus 2, then we have a plus 3. And so the change in y over change in x for this guy is going to be minus 2 over plus 3. Or simplified, because a positive and negative sign end up with a generally negative. And so the slope for this guy is also, okay, the slope for this line here is 2/3. And so if you compare the two slopes, they're the same. So the conclusion we can reach is they are indeed parallel. And it's really just that easy. You got to know the slopes, then you get to compare them. And so what about a situation where you don't have a graph to use? Well, you can still lean on the change in y over change in x, although this might be a little tricky. Now, you could use the slope formula here, but for this first one, I'm just going to take a look. So acknowledging that this is x and this is y, that's x and that's y. If we go from 4 to 14, we can just simply ask ourselves how far away are those numbers. In this case, it's going to be a plus 10. At the same time, we go from 9 to 11, that's going to be plus 2. And so the overall slope for the first one is going to be a 5 over 1, or just a 5. Now we could do the same thing here. We can compare it between negative 4, 1 and negative 2, 12. Now for this one, I'll go ahead and use the slope formula just so you can have a sense of how that's used. Like I said, I don't use this very much because I think ultimately it's more confusing. But in the end, this is just a way to calculate the changes. So I'll designate this like the first point and this like the second point. And keep in mind it is x, y, x, y. So y2 refers to the y of the second point, so that's going to be 11. And then we're going to subtract off the y from the first point, which is going to be a 1. So you got the 11 here, and you got the 1 there. So we'll put that over the calculation for the x's. So we have to go to the second point. That's what's meant by x2. So second point x. And so that's going to be a minus 2. Here's where we have to be careful because we do have to subtract per the formula, but then that second number is going to be a negative 4. So we have two negatives here. Okay, so we have 11 minus 1, which is going to be 10, which is good news. And then 2, negative, negative 4. Well, two negatives actually make a positive. And so that'll be negative 2 plus 4, which would be plus 2. So we have plus 10 over plus 2, which is going to equal 5 again. And so we see the same slopes once again. And so the natural conclusion we can reach is that they are indeed parallel. Okay, let's go to the top. Let's talk about perpendicular now. And so the thing about perpendicularity is that, again, you're comparing slopes, but now we're going to compare opposite reciprocal slopes. And so opposite just means that the signs change. And so if it was positive, then it changes to negative. If it's negative, then it changes to positive when you're comparing the two slopes. Reciprocal just means that they flip. Okay? And so if it was A over B, then it flips to B over A. Signs change, that just means like positive to negative. Right? And so we don't have new techniques or procedures. It's going to be the exact same techniques and procedures as the parallel because, again, we're just comparing slopes. The big thing here is that they're not the same. They're flipped and negated. Okay, so let's get into the example immediately. So these look generally perpendicular, but we have to back that up with some kind of calculation. In other words, we need to find slopes. Now here I kind of have the points laid out, but even if you didn't have like these nice points, you can still construct triangles. The thing is, you always want to find triangles at nice or points at nice intersection points. And so like a point like this is good, but a point like this would be very not good because you can't really tell how far in between the boxes those actually are. And so, like I said, for this example, they're laid out pretty nice. In future examples, you might have to make that adjustment. Okay, so let me just redraw those so they're a little bit better. Okay, so in terms of counting, so we have 1, 2, 3, 4, 5. So we have minus 5 and then over 2, so that's plus 2. And so the slope here, which is still change in y over change in x, is going to be negative 5 over plus 2, or just negative 5 halves. Okay, so let's compare that with this other line. And so I'm going to reuse this t point and redraw my triangle. And so we have plus 2, 1, 2, 3, 4, 5, plus 5. And so the slope would be change in y over change in x as normal. And this is going to be plus 2, wow, plus 2 over plus 5. Or two positives stay positive, so it's going to be 2/5. And so again, if you look at the two, we do have an opposite effect because that one's a positive and the bottom one's a negative. And we do have a flipping effect, so that one's 2/5 and flip to 5 halves. And so we can say, yep, perpendicular lines. Okay, so let's go down to the second example without the graph. And again, just like the previous example over here, it's just a matter of calculating the slope. And so I'm going to go change in y over change in x. We're just going to do a counting exercise. So we go from 2 to 7, that's plus 5. At the same time, we go negative 1 to plus 2, that's going to be plus 3. And so my overall slope here is going to be 5/3. Compared to this guy over here, change in y over change in x. And again, I guess let's do y2 minus y1 over x2 minus x1 just to get some very practice in here. So let's designate this the first point, that's the second point, and again, xy, xy. Okay, so second point, y is negative 4, subtract negative 2, and then we have negative 1, subtract negative 6. So lots of negatives. And that's ultimately why I don't like this technique that much, because there's so many negatives to deal with. To me, honestly, it's better just to count or easier just to count. And so either way, that's going to be plus, so we have -4 plus 2, which is a -2. And then -1 minus 6, which is going to be a positive 5. Okay? And so if you compare these two slopes, although we do have an opposite, so one is positive, one is negative, that it's not the same value, so it's not reciprocated, and so we can say it's not perpendicular. Okay? And so it's just as simple as that. Calculate the slopes, and then tell me what's going on with the slopes. If they fit the flipped and negated, then they're going to be perpendicular. If not, we got to consider them just intersecting. That's what these are. So it's neither. Okay, so let's kind of switch gears. Let's talk about congruency. We know congruency means structurally the same. In terms of what we can measure and calculate, what that really means is same distances. And so we have a couple different ways we can do that. We have the Pythagorean theorem, and really this applies to right triangles. And so just like slopes, we may have to make some triangles to make this happen. But if you're kind of cool with the making triangles to find slope, this isn't that big of a leap to use triangles to find distances. Now the Pythagorean theorem is straightforward. You guys have known this for years. We have a squared. Oh, there it is. Plus b squared is equal to c squared. And that is a 2 right there. Not a good one, but there it is. There's a 2. Now, the picture you should attach yourself to is always a right triangle, meaning there's some right angle involved. And C must be the hypotenuse, but what you use for the other two sides doesn't really matter, so I'm just going to put A here and B there because it's kind of standard. So that's a Pythagorean theorem, but we also have something called a distance formula, which the truth is, it's the same exact thing as the Pythagorean theorem, but what we call generalized to use points. And so the distance formula, if D stands for distance, the distance formula is the square root of the change in x squared plus the change in y squared. Okay. Now, the alternative version of this is that we have like x2 minus x1, which is the actual calculation, plus y2 minus y1. That should be written y2. All right, and then square it. And so it doesn't really matter which version of the distance formula you use. I prefer the first because I just like to count versus like calculate with negatives, but that's up to you. Now we could probably also make the note here that when you talk distance formula, this is more useful if you just have points. In the same sense that the Pythagorean theorem is more useful if you have right triangles, distance formula is more useful if you just have points. Allow me to explain what I mean. And so here we have two lines. The question is, are they going to be congruent? Well, we have to calculate that. You may have your own personal opinion of whether or not they look congruent, but we're going to have to back up with some kind of calculation. So let's try that one more time. Okay. So since I have the graph here, I'm just going to use Pythagorean theorem and use right triangles. And just such like slope, I have to create them first. So that's a distance of 3. 1, 2, 3, 4, 5, 6. That's a distance of 6. And so the Pythagorean theorem calculation, a squared plus b squared equals c squared, turns into 3 squared, oops, turns into 3 squared plus 6 squared equals c squared. Okay, and I'm getting 3 and 6 just off my vertical and horizontal distances, which you can count, which is why Pythagorean theorem is actually a useful tool here. 3 squared is 9, and then we have 36 for 6 squared. Okay, 9 and 36 make 45. And then if I want to get c by itself, I got a square root. And so ultimately the distance here is square root of 45. It's not useful to take this to a decimal value unless it doesn't match the other calculation or the other distance I have here. So let's just keep it as square root of 45 for now, because we're just trying to determine if they're the same. We don't really care what the actual distance is. Okay, so let's set this up a similar way. Let's create some triangles here. A triangle. We know it's right because it's horizontal and vertical. So here we have 3, 1, 2, 3, 4, 5, 6, and here we have 6. So this is probably enough right here to determine the distances are going to be the same. But we do have to show the calculation. So we do have to go ahead and take the a squared plus the b squared and equals a c squared. Let's put in 6 for a. Let's put in 3 for b. and that's equal to c squared. So that's 36 plus 9 is equal to c squared. And at this point, again, I know we can look at that and reason that those have to be the same, but proof is about showing. And so even though the calculation is going to turn out to be identical, we do have to carry that calculation out. And so when you squared 45, we can see that the distances are the same. And so since they're the same, we can conclude that yes, they are congruent. Right? So down here, much the same. Here, I think I'm going to utilize the distance formula simply because we don't have a triangle to actually yield. And so the distance formula is going to be the square root of, and I'm going to use a change in x squared plus a change in y squared. And so we can just count that. So the change in x goes from 3 to 6, and so that's going to be 3 squared. And then change in y goes from 4 to 8, and so that's going to be 4 squared. Okay, so carrying the calculation out, we have 9 plus 16. 9 plus 16 make 25. And so we have the square root of 25. That's actually a perfect square, so it'll end up being a distance of 5. For CD, let's go ahead and use maybe the long form of the distance formula. So this would be like the x2 minus x1 squared plus a y2 minus y1 squared. And so let's designate this point 1 and this point 2. Remember xy, xy. Okay, so whoops. All right, well, that didn't happen again. So x2 minus x1, and so that's going to be 8 minus 5, because again, we have the x2 point and then the x1 point. That's going to be squared. And the y2 minus y1, that'll be 11 minus 7 squared. And again, at this point, you might do a quick calculation ahead, and you realize this is going to turn out in our favor. But again, proof is about showing not just what you have in your head, but what you can show on paper. And so this will be 3 squared. 8 minus 5 is, of course, 3. 11 minus 7 is 4 squared. And so we have 9 plus 16 again, which means we have the square root of 25, which means we just have the CD distance equaling 5. Okay, so we have this to be the AB distance. We have this to be the CD distance. And since those are the same value, we can say that once again, yep, they are indeed congruent. And so, guys, that's it. That's like the cheat sheet, right? And so, if you want parallel, you have to get the slopes by whatever means necessary. Compare them. If they're the same, they're parallel. If not, they aren't. For perpendicular, we're going to also find the slope. So, same technique. If they're opposite and reciprocals, which means the sign is changed, one's positive, one's negative, and it's been flipped on the fraction, we can say they're perpendicular. If they're not, then we can say that they're not. For distances, we're always checking. For congruency, we're checking distances. Pythagorean theorem is fine if you can construct a right triangle. If not, use a distance formula. If they're the same distance, even if you don't know the exact value of the distance, if they're both square roots of 45, of course they have to be the same distance. We can say they're congruent. Otherwise, we can use a couple different forms of the distance formula and say the same thing. Okay, and so as a way of consolidating the consolidation, let's flip it to the back. So how do you prove lines are parallel? Well, that's pretty straightforward. If lines are parallel, then the slopes of the lines are, let's say, the same. Then lines are parallel. To prove lines are perpendicular, if the slopes of lines are opposite reciprocals, which again just means negated and then flipped. Lines are perpendicular, and if the distances of the segments are the same, then the lines are congruent, right? So I know those are kind of long, guys, but those are how consolidation notes sometimes go. And so last thing on the agenda today is to take your quiz. So thank you very much and have a great day.